Hello, in this video I'll try to explain interfacing of DAC, that is digital to analog converter, to LPC 1768 microcontroller to generate triangular, ramp and square waveforms. So actually the LPC 1768 consists inbuilt DAC module. So you need not to interface digital to analog converter externally to the LPC 1768 microcontroller, since the microcontroller itself consists inbuilt DAC module. So and this inbuilt DAC module consists a DACR called DAC register, that is digital to analog converter register, which is of size 10 bits. Okay, so here we are going to use 26th pin of port 0 as an analog output pin. The output of the DAC corresponds to 26th of port 0, and since this particular pin can perform multiple functions, like by default it's going to perform general purpose input output and the first alternative function and second alternative function and the third alternative function. So since the analog output corresponds to the second alternative function, the 26th pin of port 0 should be configured as analog output pin by choosing the appropriate value to the 20th and 21st bits of pin selection 1 register. Since we have to configure the functionality of this pin, the associated pin selection register must be used. Here the pin selection 1 register should be used to configure the 26th pin of port 0 as a out pin. Okay, so to configure that, the 20th position of the pin selection register should be 0, whereas 21st position of the pin selection register should be 1. Okay, this is about the 26th pin of port 0 and their different functionalities. Now coming to the DAC register, which is of 32-bit size, where the first 6th bit of this DAC is reserved, that is bit position from 0 to 5th is reserved, whereas bit position from 16 to 15, sorry, from 6 to 15, these 10 bits are actually used to store a value. So whatever the binary value or the digital value you are going to place at 6 to 15th position of DAC register is going to convert into a corresponding analog value by the inbuilt DAC module, and that analog value can be displayed, or analog value can be measured at the A out pin. Okay, so that will be throw out to the outside world through an A out pin, whereas the 16th pin is reserved for bias, and similarly from 17 to 31st bit of DAC register is also reserved. So this is about DAC register. So whatever the digital value you have to convert into a corresponding analog value, that digital value should be placed in the bit position from 6 to 15 of DAC register. So this is about the inbuilt DAC module. So looking to the schematic of the DAC module. So this is a DAC module which consists of DAC register. Here the DAC register essentially consists of a 32-bit register, but we have to use only the bit position from 6 to 50. That is only 10 bits among the 32 will be used to place a digital value. That digital value is going to converting into corresponding analog values, and that analog output can be observed at A out pin. So and also this DAC module connect to V reference positive and V reference negative. Essentially the V reference negative is 0 and V reference positive most of the time it is around 3.3 volts. Okay, so at any point of time the output value, the analog output value, can be calculated by using this formula. The voltage at the analog output pin is equals to value multiplied by V reference positive minus V reference negative divided by 1024 plus V reference negative. Here the value refers whatever the binary values you are going to place at the DAC register. So that value can vary from minimum 0 to maximum 1023 in decimal, and this 1024 is because since we are using 10-bit register, 10-bit place or 10 bits for DAC to place the value in the DAC register. 2 power 10 is 1024, so 1024 different values can be placed in the 10 placed in those 10 positions of the DAC register. Okay, and since the value of V reference negative is 0, the formula is going to reduce as V A out is equals to value multiplied by reference positive divided by 1024. By knowing the value, whatever the value placed at the DAC register, you can identify what is the corresponding output voltage that is going to produce at the output terminal of the DAC module. Okay, so this is about the internal schematic of DAC module, and also you look at that the 26th pin of port 0 is dedicated as analog output pin, and it is very essential to configure this pin as analog output pin with help of pin selection 1 register. Now let us look into the algorithm of the program. So here essentially you have to initialize the DAC output pin as A out by loading 10 to the appropriate pin selection register. Here, since we identified, that means the DAC output pin is connected to 26th pin of port 0, and this corresponds to port 0, therefore, and the 26th pin is in between 16 to 31. So obviously the corresponding pin selection register is pin selection 1 register. So with the help of pin selection 1 register, you have to change the functionality of 26th pin as A out pin. So since the A out corresponds to second alternative function, the value that's supposed to be forced in 21st and 20th position is 1 0 respectively. Okay, and therefore the corresponding hexadecimal value become F F E F F F F F. This is the one way, or else alternatively we can directly load 1 to the 21st position of pin selection 1 register. So either the way you can configure this 26th pin of port 0 as A output pin. So this is the first step, and in the second step, whatever the value you have to convert into a corresponding analog value, that digital value should be placed in DAC register from 6th bit position. Okay, because since 0 to 5th bit, first 6th bit, that is 0 to 5th bit of DAC register is reserved for some other purpose, and from 6th to 15th bit of DAC register is supposed to be used as place where the value is supposed to be stored. So you have to store that value from 6th bit position. So most of the time this is the instruction is going to use. Here I refers the value, digital value is supposed to be converted, so that I value is shifted towards left direction by 6th position in order to place the value, or in order to match this value to the 6th bit position of the DAC register. And this DAC register comes under the structure called LPC_DAC. Okay, this is an instruction or the statement to place the value, that value here an arbitrary value I. So to place this digital value in DAC register, so this is the statement supposed to be used. Okay, this is about the steps. Now coming to the program. So in this program, let us try to understand how to generate the triangular waveform. So in triangular waveform is nothing but the voltage level is linearly increased from minimum value, that is from 0 to maximum value. Here the maximum value is 3.3 volts, and once the voltage reaches to the maximum value, it has to linearly decrease from maximum value to minimum value. Okay, so this is about the triangular waveform. So now coming to the program. So here hash include LPC17xx.h is an header file. All the associated register of LPC1768 will be under this header file, and we are defining two global constants. So one of the global constant is voltage. So and that voltage we are going to assign a constant value 1024. Since the DAC register is of 10 bit and maximum value that can be stored to the DAC register is 1024 in decimal. Okay, that's why that value is going to stored in voltage. And another global constant is frequency. Actually it is not. Okay, another global constant is defined as a frequency. For this decimal value 10 is loaded, and so this is the 10 refers how frequently, okay, what's the span of time between one value to the other value. Okay, so that we are going to take a very small span of time between one bit one step value to the other step value. Now is the initialization of the main program. So we are declaring two variables which is of unsigned integer and they are 32-bit size of type. Okay, so unsigned integer type of 32-bit size. The name of the variable is I. Similarly, an unsigned integer 32-bit size variable with the name m is declared here, and this is in this case the variable I and m can load only positive value, and this cannot be stored the negative values here. And now this is very important statement where we are going to configure the 26th pin of port 0 as a out pin. So here this indicates 21st position of pin selection 1 register is set as 1, and that is going to logically odd with the original content of the pin selection 1 register. So thereby you are altering only that particular bit position, and remaining bit positions will be unaltered. So you are ensuring that only 26th pin of port 0 change its functionality, and remaining pins of port 0 will be functionality of the remaining pins of port 0 is remains same. Okay, so this is about the statement which is very important to configure the functionality of the pin. Now we are going to an infinite loop. Okay, here since we have to generate the triangular wave, we have to linearly increase the voltage level from minimum to maximum value. So this is a for loop where initially the value of I is 0, and we are comparing whether this I is less than voltage. Here voltage refers 1024, means we have to compare whether this I is less than 1024, means maximum this I can hold 1023, and if as long as this condition is satisfied, the value of I will be incremented. Initially the value of I is 0. Now that value is shifted left direction towards 6-bit position in order to match the value to the 6th position of the DAC register, and that value will be placed in the DAC register. Okay, and this DAC register comes under the structure LPC_DAC. Okay, now after some amount of settling time, this value will going to convert into a corresponding analog value, and that will be flow through, or that will be displayed, or that will be that can be observed in analog output pin. And now the next value, that means before uploading the next value, so we are elapsing some amount of time. Here the time units are 10 time, that means very small time units are taken. So that is the time difference between the first value to the second value. Now once this time is elapsed, then the value of I will be incremented. Okay, that incremented value is kept in the DAC register, and we have to wait for a small short span of time. So likewise till the value reaches to the maximum, till the I value reaches to the maximum, that is 1023, this loop will be repeated. So the output expected is from 0 to 3.3 volts. Once the I value reaches 1024, so the for loop statement returns with false. So obviously this for loop statement won't be executed. Now the another set of, that means alternative for loop is going to check here. So here we are going to compare, initialize the I variable I with the maximum value, that is voltage, it's nothing but 1024, and we are going to compare whether this I is greater than 0. As long as I is greater than 0, the value of I is going to decremented. Okay, now and that value is again loaded to the particular position of the DAC register. So now initially the value of I is maximum, and after first iteration the value of I will be decremented by 1, so that linearly the analog output pin voltage will keep on decremented. So therefore thereby we can expect a triangular waveform at the analog output pin. So this is about the program to generate triangular waveform, and this triangular waveform can be observed from 26th pin of port 0 with the help of CRO or multimeter. Now let us look into the program to generate the ramp wave. Okay, it is most similar to the triangular wave, where the loop which is responsible to generate the linear value from maximum to minimum is eliminated. That's all. Okay, so here only we are using a loop with initialization of the 0 value, and we are comparing with maximum value, that is 1024, and as long as this condition is true, the I value will be keep on incremented and that value is placed on the DAC register, so that we can expect the value of analog output voltage value will be keep on increased from minimum value to maximum value. Once it reaches the maximum value, again the same for loop will be executed with I initialized as 0. So the once it reaches the maximum voltage, immediately in the next span of time, the output voltage becomes 0. Okay, so this is to generate a positive ramp. Similarly, you can generate a negative ramp by initializing the I value as voltage, and you have to compare whether I is greater than 0, and you have to decrement the value of I for each iteration. Thereby you can even generate a negative ramp wave. This is how to generate ramp wave with the help of inbuilt DAC. Similarly, let us look into the program to generate a square waveform. So here we have included an header file, and the maximum value of the voltage with a global constant voltage is declared as 1024, because we are using 10-bit DAC register, so 2 power 10 is 1024, and we are defining another global constant name frequency is equals to 100. Okay, now this in square wave we have to post only two possible value, that means the minimum value and maximum value. Only two possible values must be placed in the DAC register, and we have to give some sufficient delay between these two alternative values. Okay, the delay is around 10 time units, sorry 100 time units. Now we are declaring one, this is an initialization of the main program, and here we are declaring a variable which is of unsigned integer which reserves 32-bit in size. Okay, now this is a statement to configure the 26th pin of port 0 as a out pin. Now we are going to enter to the infinite loop, where initially the DAC register is placed with voltage by 2 value, that means half of the maximum value is going to place at DAC register. Therefore the minimum value at square wave you are going to get as 1.65 volt, and we have to wait for certain span of time. Here the time is taken as 100 time units. After span of time, your DAC register is placed with the maximum value. The maximum value is 1024. Okay, so this value is placed in the DAC register, and have to wait for around 100 unit of time. Thereby the analog output pin is going to switch between 3.3 volt to 1.65 volts. So this is how to generate a square wave with the help of inbuilt DAC. Okay, so that's all about the program.